There we go. Okay, so typically when I give this session, I always ask the question like, who is confident enough to talk about memory management and who is 100% sure that they can explain how .NET memory management works, knows about all or at least some of the ins and outs of .NET memory management? Anyone? Good. I will also not put my hand up because I probably also don't know everything that is in there, and that will become more clear when we look at the source code of the garbage collector. Don't worry, we'll just look at it. But the main idea of this talk is to give you an idea of how .NET memory management works by giving you a 10-minute introduction, like a crash course on the general way of working with .NET memory in your applications. And then we'll look at a couple of tips to make you help .NET in becoming more performant, behave better on most servers and desktop computers and mobile apps and so on. And look at a couple of those quirks that exist so that you are aware that those exist and you can take those into your day-to-day job as well. So the .NET runtime, if you look at the .NET runtime itself, you will see that it does a lot of things. So when you double-click a console application or you launch an ASP.NET application, there's a couple of things that happen in the .NET runtime. There's just-in-time compilation, where it will take the IL, intermediate language code, and translate it into machine code, run that thing on your server or on your desktop, and the application will start because of that. Now, all of that is machine code, and you have been developing in this rich object model and so on with types. You have a person, you have a customer, an address, and things like that. So the .NET runtime makes sure that you have some type safety in your runtime environment as well, so that you can actually work with those things when running. There's exception handling, there's security in there, threat management, and so on. Those are not the topics of today, so memory management and garbage collection only, although every once in a while there will be a link with one of those other things that the .NET runtime does for you. Now, you know there's classic .NET framework or the standard .NET runtime, as well as core CLR and those things. What I am going to talk about today is valid for both of those runtimes. One is a little bit newer than the other one and has more features to do things around memory management, but the general principles are the same for both. So with that, let's go. Memory management and garbage collection in .NET is quite interesting because you get virtually unlimited memory. You just allocate things in your application and you get the memory in your application and you can use it. Any one of you doing C or C++ or things like that? Yeah. So you probably know that you have to allocate memory, ask the operating system to give you some spots in memory. Then you can allocate your variables in there. And then once you're done, if you're a good developer, you give the memory back to the operating system because otherwise you have a huge memory leak in your application or your computer will crash. So in .NET, you get virtually unlimited memory for free. It's in there. It gives you a big chunk of pre-allocated memory. And in that pre-allocated memory, .NET does the allocations for you. So it's managed by .NET, and that's why it's called managed code in effect. Now, the runtime manages this. You don't have to worry about .NET allocating things in memory and so on. You just write your code, and the garbage collector and memory management will do the things that you expect it to do in there. At some point, when some variables are no longer being used, there will be the garbage collector running, and the garbage collector will check, is this memory space still in use? And if not, it will free it up so that you can reuse it for something else, and the virtually unlimited memory story stays the same story. When you allocate something in .NET, where you are allocating your objects is in a managed heap. So when your application starts, there's a big chunk of memory being reserved in the operating system, and you start allocating in the .NET runtime, and the .NET runtime just uses that big chunk of memory to store your objects in. Allocating is really fast because of that, because the block is already there. It just has to add a pointer in there, and that's pretty much it. There's no round tripping to the operating system to ask for more memory or release the memory and so on, although there are cases where that step will occur, but you don't have to worry about that. If you look at any .NET application, you will also see that there is some unmanaged memory in use as well. Those are typically the things where .NET does its own stuff. .NET needs to store some things about your application as well. If you do GDI or you have a WPF application and there's some graphic buffers involved, those will typically live in unmanaged. But other than that, mostly all of your memory will be in this managed heap. Now, At some point, the garbage collector will run, and the garbage collector will scan the entire object graph that is in this managed heap, this big block of memory. And it will check, is this object still in use? Can I reclaim the memory and make it available for future use in there? The way it does that is by typically just scanning every object that is in there and doing some sort of reference counting. It checks, is this object still reachable from any point in my current execution stack? If not, it will be collected and the memory can be reclaimed. If it is still being used or being referenced by something that is reachable in your entire application, the object will stay in memory. Now, with computers and laptops, mine has, I think, 32 gigabytes. That's a lot of memory. If I do a 64-bit .NET application, that's a lot of memory to scan, so it will take some time. If I use all that memory on my machine with small little objects that the garbage collector has to scan, that will take some time, and even in smaller memory footprints, that will take some time. So Microsoft and a lot of managed languages like Java, the JVM for example, do this as well. They split this managed heap, this big chunk of memory, into different generations. And the way that works is when you allocate something, you start a method and at the first line you instantiate a new variable. What will happen is that variable will be allocated in generation 0. Because .NET and the CLR basically thinks that most variables, and in effect this is the case as well, most variables will go out of scope once you reach the end of the method. Because the variable was just temporary in there, and at the end of the method it will go out of scope, and generation 0 can really hold those short-lived objects. And the garbage collector can run really frequently on those because it will typically be a smaller set of objects to scan because it's in the scope of one method or a couple of methods, and it's smaller to scan. When your object is still in use, it will move to generation 1. Why? Because that's a generation where the garbage collector will run less frequently because it knows, okay, the variable is not some local variable, it's still in use, so I'll keep it and I'll check it at a later point in time again. If the object can be removed from memory, so at the end of your method, for example, the object will be reclaimed by the garbage collector. Same thing happens in generation 1, although less frequently, but it will scan all the objects in generation 1. If they are still in use, they will go to generation 2, the long-lived objects, basically. If not, they will be removed from memory again. Again, Gen 2 will run garbage collection as well, but even less frequently, because if you have a long-lived object, the chances that whenever you run the garbage collector frequently, the chances that those objects have to be reclaimed are smaller, so it will run less frequently on generation 2 in there. In Gen 2, when the garbage collector runs and your object is still in use, it will just stay in generation 2. If not, of course, it will be reclaimed as well. So that's pretty much how that managed heap works. There is 1/3 generation or 1/3 heap, and that is the large object heap. So this is a special place where large objects go live. If you have an array that contains the entire population of the Netherlands, for example, as strings and names and so on, that will probably go and live on the large object heap because .NET thinks, okay, this is just too big to reclaim and too big to check all the different pointers. I'll just put it in this large object heap. This is almost a trash can or a bin where they store those things. It will actually do garbage collection on the large object heap as well. So when Gen 2 collection happens, the large object heap will be collected as well. Although there is one difference. With all the other heaps, you get defragmentation of the memory space. Anyone old enough to remember the defragmenter? Yes. So what happens is, if you have your memory space and you allocate things in the memory space, if you at some point require a big chunk of memory, say you want this chunk of memory, it never fits anywhere. So in Gen 0, Gen 1, and Gen 2, a fragmentation or compaction will run so that your big object can fit in that managed heap that is available. On the large object heap, by default, this defragmentation is not happening. So what will happen if I want to allocate a really large object in this large object heap is I get an out of memory exception because the large object heap is full and this thing cannot fit as one big block in this piece of memory. So that's pretty much what happens there. Right, everyone, any questions so far? Good. The .NET garbage collector is something that everyone knows and has heard about and so on. The problem is nobody knows or appears to know when it runs. I don't know, there's a couple of bloggers out there that have been testing and experimenting when it runs, and typically the observations are that when there's memory pressure, when there's an out of memory condition, it will either allocate more memory or run the garbage collector to reclaim memory in your application. When you do a significant allocation, say that you are loading everyone in the Netherlands from your database and storing them as domain objects somewhere in your application, that's probably going to be a large allocation, and the garbage collector will run right after that. When allocation fails for some reason, could be because there's no big chunk of memory available, the garbage collector will run, compact things in Gen 0, 1, and 2 to make sure that the object fits in memory. And then there's a couple of other conditions where you can run the garbage collector, either when you are profiling or when you call gc.collect in your source code. Don't do this, by the way, but you can force it to run. Also on Windows, when your application moves to the background, when it sees you're not focusing on your WinForms application, for example, garbage collection will typically happen so that memory can be compacted again. One important thing, if you have lots of memory, 64-bit application, and you tune .NET a little bit, you could land in the case where the garbage collector doesn't even run, because there's sufficient memory available and the garbage collector will just not run. So it's not guaranteed that it will run. That's also an important one to take away. Now, I promised you that we would look at the garbage collector source codes. I'll load it. It's on GitHub. It is in C and C++, I think. And it is some 60,000 lines of code. I am still zooming. So this is the garbage collector. If you can figure out when it runs, please tell me. I would like to know. Also, if you feel like replacing the garbage collector in .NET, you can actually do this. There's an environment variable that you can set and basically say, okay, I want to plug in my own garbage collector and run my own garbage collector. So if you feel like writing 60,000 lines of code, you can do so. So far, searching around on the internet, I found one alternative implementation of the garbage collector, which is the no garbage collector. So they basically just store whatever they have in memory and keep allocating more memory, and it will crash eventually. So there's not a lot of people who have attempted this, but it is possible. Right. As we already saw, that the .NET garbage collector runs very often for generation 0. Why? Typically, it's only in the scope of one method or one class or a couple of methods and so on. So there will be fewer references, and it's really quick to collect those objects from memory. Typically, local variables, if you do a web request response in an ASP.NET application, the request and the response will be typically the unit where garbage collection will probably happen for generation 0. The higher you go up the generations, if you go to Gen 1 or Gen 2, typically the objects will have more references in memory. It will be much slower to figure out, is this object still in use? An important thing is that the garbage collector pauses your application when it is running garbage collection. Typically, for most collections, this will be almost not noticeable. It will be a couple of milliseconds, and you will not see that the garbage collector is pausing your application. But I have seen server-side applications where, for example, a Gen 2 collection takes 5 seconds. And that may not sound bad, but it also means that your server is basically not responding for 5 seconds. And that is bad. Depending on the type of application you are building, you don't want to go there. Funny thing, before I joined JetBrains, I was on the NuGet team in Microsoft. And our search service, so the thing running search in NuGets, we have seen garbage collector pauses there of up to 2 minutes, which is mind-blowing. Reason for that, if you want to know, find me with a beer afterwards. Let's just say really big byte arrays are not really nice to have in your .NET applications. Anyway, back to the actual stuff. Yeah.
Is there a reason why the garbage collector runs on the main thread or pause your application? Like, is there no reason why it could run asynchronously?
Well, so the garbage collector has to scan all the objects that you have in memory, and while it is running, if you make changes to memory, it would have to start all over again because maybe you added a new reference or allocated something and something may have changed that influences the tree of objects that should be cleaned out. So that's why this doesn't happen. Although there is asynchronous collection, there's background garbage collection, which is enabled by default nowadays in .NET, and it will basically spin up an additional thread or a couple of additional threads if you have multi-core applications. And it will run concurrently with your application. It will pause just one thread, and then this garbage collector thread will collect everything that that thread is holding on to. So it will still pause, but it will be less noticeable because if you have a 4-core machine, there will be one core that is basically paused, and the other cores still keep processing whatever they are doing, unless you have variables that are shared across threads and so on. So there's always the edge cases, but it happens today. Garbage collection is usually asynchronous, but not always. Right, this brings me to this interesting blog post that I saw yesterday. I don't know if you saw it circling around on Twitter. It's from the developer who wrote the Fira code editor font. Don't know if you know this one, but if you're editing, you can have a nice console font that has ligatures, and it's really nice. But he's basically disappointed with software that we are writing today. Basically, the summary of the entire post is developers write shitty code, and we keep adding more layers of shit on top of it. That's the summary of the blog post. And I think he's right, and I think a lot of those things, not all of them, come from the fact that we take a lot of things for granted. Like there's a garbage collector and memory management will help our application. We don't have to think about those things. But we as developers can actually help .NET manage our memory more efficiently. And that's the remainder of the talk here. Interesting post, by the way. Really read it. It's the best rant I've read last week. Right, so what we want to do is help the garbage collector collect more efficiently, and if you see those pauses of 1 or 2 seconds or maybe up to 2 minutes, you want to avoid those pauses in your application because they're not pleasant. The customers will complain, you will complain, you may think that your server is down, maybe automatically reboot because it's not responding, so you don't want to do that. We want to help the garbage collector, and we can do that in a couple of ways. One is optimizing allocations. Don't allocate, the garbage collector will be happy, but you also have no application, so that's not really an option. But if you don't have to allocate, maybe you should not allocate. If you do have to allocate, you may want to use a struct instead of a class whenever it makes sense, so that the variable is actually allocated on the stack and not on this managed heap where the garbage collector has to do its thing. In .NET Core, you can use span of t, for example. That's another struct that helps you allocate on the stack instead of the heap. You can do things like object pooling and so on. I'll dive into that a little later. But basically, when it makes sense, you may not want to give work to the garbage collector, but just allocate on the stack, which is where elements are added. And when your method goes out of scope, the entire stack disappears and all the objects disappear as well. Making use of iDisposable and the using statements can also help clean up references and make the garbage collection process more efficient. You can use weak references as well. Anyone know what those are? I don't think a lot of people are using them, but weak references are basically an object that wraps another object, but you don't know if that wrapped object will always be there. You basically tell the runtime, look, this is a weak reference. If the object is there, fine, just give me the object. If it's not, here's the code to recreate the object. And that could be nice if you're building a cache layer or something like that, where you just allocate a cache variable, but if it disappears from memory when the garbage collector runs, it's fine, you can recreate it based on the code that you have. Weak references, not a lot of people are using them. They may make sense in your application. Bottom line of those is that the garbage collector will say, it's a weak reference, I'll clean it up, and I'll not even check what is referencing this thing. So that's also a little bit dangerous. Another dangerous thing is writing your own finalizers. Anyone did that? Anyone wanted to kill themselves after that? Or, yeah. Finalizers are really good because that's the last step before garbage collection really happens, where you can do some cleaning, clean up managed or unmanaged resources and so on. But if you do something wrong there, the garbage collector will basically say, you were responsible for cleaning this thing up, and it will not do it itself. So if you forget something, the object will stay in memory. So beware with that thing. Also, I'll show this during the demo as well. Those will always go to a new generation, which means that they will have to be collected twice instead of once. Right, let's help the garbage collector a little bit. By the way, until what time can I run?
The 8-ish.
Right, weak references, anyone want to see those? Okay, 2, 3, yeah. Disposables? Everyone, fine. Right, let's start with the weak references. I have a weak reference demo, and by the way, if you download the slides or search me on GitHub, you will find all these demos on GitHub, so you can try them yourself. And you will find that in the code, I have added console.writelines with what you can do and what you can profile to look at what is happening in there. So basically, weak references. What I'm doing is creating a new object called cache, and I'm adding 20 random objects into that thing. Then at some point, I will run garbage collection, and then I will check how many of those objects that I initially created in my cache have had to be recreated because the reference was cleaned up by the garbage collector. So that's the control code of this thing. Now let's look at the cache instead. The cache itself is a normal class that holds a dictionary of integers. So I have an index of the thing that I'm caching and a weak reference to some data object. The interesting thing is that I'm storing weak references there because those weak references, as I told you, will be cleaned up at some time. So when I create this new cache, I simply create new data objects and add them inside a weak reference. I have a count, I have a regeneration count where I keep track of how many times the objects have had to be regenerated and so on. And when my weak reference does not exist, which is this check, I will recreate my data. So that's my cache object. Nothing really spectacular, but just to show you that when the garbage collector runs, some of these objects, and every time I do this demo, other objects will be cleaned, but some objects in my cache will be cleaned, and at some point this method will be called as well, where new objects will be regenerated. So if I would run this, I'll do that. If I would run this, and at some point the application actually runs, yes, I can run this demo, and it says, okay, I now generated 20 objects in cache, then I run again, and then I check which objects have had to be regenerated. As you can see, some objects have had to be regenerated because the weak reference was cleaned up by the garbage collector. In fact, if you open a profiler, let me unzoom there. If you open up a profiler and take a snapshot right before garbage collection and right after garbage collection, you will also see that in the first snapshot, if I search for data objects, I actually have weak reference of data. So this one, I have 20 of those in memory, which is what my code was doing. But after I run the garbage collector, you will see that the number of objects that are a weak reference of data, so this one, the fourth one there from the bottom, now only has 20. Interesting. So could happen, or I took this snapshot at the wrong moment. That should be less. Damn it. Did I open? I can prove that I'm still right. I can compare these two snapshots. Now, the reason the weak reference is, of course, still there because the weak reference was holding on to my data, and I should check the data object instead. But if I compare these two snapshots, you will actually see that those weak references, I had 7 that survived the garbage collection, but 13 of them had to be regenerated because the garbage collector cleaned them out. So that's what this thing did. It's not the most spectacular demo, I know, but it's a talk about memory management, so bear with me. Right, so that's weak references, and it's basically just the concept of having a wrapper around an object, and when garbage collector runs, the object may be gone from memory, even if you expect it to be there. And in some cases, it may be useful. In other cases, I'm pretty sure you don't want to go there. Now, I also have a sample disposable. Forget the fact that this thing is there, so this line is still running, but this line is not there. I basically have an object that wraps a file stream and that wraps an integer pointer somewhere to unmanaged memory in my application and so on. What I will be doing in this demo is create 10,000 or 20,000 of these objects. store them in a list, and then run the garbage collector to see what happens if that list is cleared. So that's what my control code does here. What I do is I create a file so that I have a file stream that I can reference, and then I run 10,000 allocations where I create a new sample disposable linking to this file on my machine. Then I clear out my lists, and then I run the garbage collector. Normally, you would expect that the garbage collection would clean out all the objects and all the file streams and so on from memory because I'm in .NET and .NET does the memory management for me, right? Well, the thing is, it doesn't. If you look at the snapshot, I'll not run this because it's the most boring console application ever. But if you look at the snapshots that I took one snapshot when I just allocated 10,000 objects just to verify that 10,000 of those objects are in memory. And as you can see, I have, of course, my list of sample disposables. The list of sample disposable internally uses an array of sample disposables. And of course, I have the objects themselves. If you look at those, indeed, I have one list containing two arrays because internally the list distributes it across multiple arrays. And I have 10,000 of those sample disposable objects in there. Then I forced the garbage collector to run, and I went into my second snapshot. So in the second snapshot, I would expect that all my sample disposables are gone. So the list and the array are still there. But if I search for my sample disposable, you will see that that's the only thing that appears to be in memory. And I'm really saying that appears to be in memory because my sample disposables are still in memory. If I look at the automatic inspections in this profiler, you will see that all of my sample disposables, those 10,000s, are marked as finalizable. So they have been moved to this special generation where the garbage collector keeps track of objects that will collect during the next garbage collection cycle. So it checked all the references, noticed that in managed memory everything was okay and everything was cleaned up, so it moved those to the finalizable objects because it saw that I was still using file streams and these integer pointers underlying, which are references that have to be cleaned up as well. So the objects are still in memory, and my objects will have to be scanned by the garbage collector twice to disappear from memory. Proof of that is in my third snapshot here. If you search for a sample disposable, they will not be in there, and in the inspections of the finalizable objects, you will see that in this round they have indeed been finalized. So that's good, they are gone from memory, but it took the garbage collector 2 runs to actually remove them from memory. So the better way to do this is by making our sample disposable really idisposable. And in my dispose pattern, dispose of my file stream and free this managed resource as well, unmanaged resource as well. Reason for that is I know how the object works, so I'm helping the garbage collector cleaning up references so that ideally this object can be collected in one generation and not in 2 steps. And that's what happens if I run my second demo here. Again, I create a list of 10,000 disposables. Then for each disposable, I call .dispose, or it's basically 10,000 using statements that I've generated here. And then I run the garbage collector. What I would expect is that the objects are now gone from memory in 1 step. And again, if we look at the profiler, in the first round we now have, again, 10,000 disposables or sample disposable objects. But in the snapshot that I took after garbage collection, you will see that those objects are really gone from memory. It's just the array that is still there. And if you look at the inspections, there's also no more finalizable objects in there either. So they have really been removed in 1 step in this case. So that's good. We helped the garbage collector and we made it more efficient because it only had to do the work once. So please, if you have file streams, other disposable objects in your objects, make them disposable as well and call that dispose methods either manually or using a using statement. That's the lesson or the key takeaway of this one. Any questions so far? All right. Good. Let's look at allocations. So we looked at the cleaning up part. Now let's see what happens or how we can reduce the number of allocations that we are making. When is memory allocated? Typically not for things like integers, booleans, structs, decimals, and all those base types that you have. Those are allocated on the heap, on the stack, not on the heap. The heap is where the garbage collector has to do work. The stack is where you basically put something on a stack. You may put more things on the stack, and at the end of your method, the stack will be empty, and those things are gone from memory as well. When you are using reference types, your own person object, your address object, things like that, those typically live on the heap because they are objects and you knew them, so that means they will be allocated on the heap. The properties of that object, if there's a string on there, if a person has an address, there will be a person and an address allocated on the heap, and the reference will be kept by the runtime as well. Those are really visible because if you look at your own code, you will see the new statements, or you know that you have an IOC container creating the objects and so on. So they are very, very visible. What a lot of people don't know is that there's also invisible allocations happening in .NET. The perfect example is boxing. Anyone know what boxing is? All right. Typically, imagine you have an integer. Just look at the code. You have an integer and we assign 42 to it. What will happen is if we cast that to an object or wrap it into a reference type, we are actually wrapping it. We are putting this integer into a reference type box, and we are allocating the reference type. So now we actually have two allocations because we have the allocation on the stack, our actual integer, but also the reference type, which is wrapping that integer or the reference to that integer. Unboxing, by the way, if you recreate your integer based on that object, is not an allocation, because it will give you the position on the stack, but there will be CPU effort in following the reference, and although it's only a couple of cycles, you may not want to do this because you're wasting CPU in this case, but that's not memory management. So boxing is one that you will see in a lot of applications. You cannot always avoid it, but if you can, please avoid it because you're really wasting memory and putting strain on the garbage collector and making it work for you, and you want more resources for your actual application. When you're using lambdas, closures, things like that, when you're using tasks and async await and things like that, there's a lot of hidden allocations going on. We will look at that in a little bit. But you will see if you do an async await or you do a link statement or whatever, some hidden classes are generated and also allocated on the heap and have to be managed by the garbage collector as well. So you may not see them in your source code, but the intermediate language that is created from your source code will contain those classes, and they will be there. Params arrays, those are really interesting. I will show you the code and you will understand what is happening, but those also create a couple of hidden allocations. How do you find hidden allocations? Typically past experience. You learn and you see something is happening and you learn those things and you try to no longer do those things. If you don't have that experience or you still feel like I want to look into these things, narrator there, by the way, is always look into those things because no one ever has all the experience to know all the edge cases and so on. So always either look at the intermediate language that is generated, add a profiler, or use some tooling that actually knows about these things and covers all the edge cases and so on as well. If you're using ReSharper, there's a heap allocations plugin which will give you a nice squiggly when you are doing a hidden allocation. Roslyn has a similar one if you're not using ReSharper, where they scan for hidden allocations and also give you a squiggly and a warning that you may not be doing what you think you are doing. Now, one thing, and that's true for the entire talk as well, don't do premature optimizations. If you have a variable and you allocate 10,000 variables at the start of a method and at the end of the method they are removed from memory, you may not even have to optimize because the garbage collector will run and it will be quite fast to collect those objects as well. So always try to measure using a profiler before you start optimizing. I really want that to be the key takeaway of this thing. Anyway, hidden allocations. Let's look at a couple. By the way, I'm using ReSharper here, and ReSharper has a nice tool window called the IL viewer. And what the IL viewer will do is give you a nice view of your C# code, but the intermediate language representation of that thing. So if I select this call, I will also select the things in the intermediate language editor and I can see what is happening behind the scenes there. Now let's close this one because that's not really important. And let's look at some hidden allocations. I have some examples here. So I told you about the boxing, right? Allocating an integer and then boxing it into an object. Well, if you look at the intermediate language for this line of code, you will see that I'm actually loading I from the stack, then boxing it into a system.int32 and so on. So I'm really allocating something. If you look at the description in the tooltip that appears, you actually see that we are converting a value type to an object reference type. So it means we are allocating. So this is one way of seeing that we are putting stuff in the managed heap. Now that's a simple example. Let's look at another one, the params array. That's one of my favorites. So who of you writes codes that does something like this, where you have some methods that takes a params array of some data? I think everyone has been writing those in their career. Yep. What if you call it without any parameters? So you take this thing, but it means the array can also be empty. What if you call it like this? Well, turns out, if we look at the IL code for this, that when we call the methods without any arguments, we are still creating a new array of string, an empty one, but we are still allocating an empty array of string. So maybe, instead of calling my real methods like this, the one that actually takes the data, maybe I want to create an overload that just takes no arguments, so that I'm optimizing this and no hidden array has to be allocated in there. That's one way of fixing this one. Let's undo that. Yeah. Another one, link and lambdas and so on. Those are really, really nice. This looks like nice code, right? If you look at the method we have here, and can you see it in the back? Yeah, okay, fine. So this method does an average within bounds. So basically it takes an array of integers and imagine it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I also give it a minimum and a maximum. So I say minimum 2 and maximum 4. It will calculate the average of all the elements in the array that are between those two values, just to have some sample code that does something. So I could write complicated for each statement and so on, or simply use some link, because link is really nice and useful and it's always good to use, right? Well, this makes perfect sense. I create a variable called filtered and I select from inputs where x larger than my minimum and smaller than my maximum, and then I select x, and then based on that I call .average. Nothing complicated to it, and it really looks nice. It even reads nice. It conveys the message of what I'm trying to achieve here. The thing is, you know that link only executes, only evaluates whatever you have when you materialize the things that you are creating. So only when we call .average, it is actually doing something. Only when we call .average, this code will be executed. When you do a toList, when you do a .count, a .any or whatever, those are the only moments where you will actually evaluate the link statement that you wrote. So in order to be able to do that, we will have to capture some values. We will have to know what our inputs are. We will have to know what the minimum is and what the maximum is, because right in between, I can say minimum equals 9, and I still want to have the minimum that I originally allocated there, right? Things can change in between, my query can even change in between, so I want to make sure that at the moment this thing was created, that those values are in there so that I can use them as well. Well, turns out if we look at the intermediate language codes, that at the start of my method here, I am actually, so this method is called demo random. Yes, I'm creating a new object, and this is really saying I'm allocating something, and the object is of type display class 3_0. I didn't write it, but the compiler wrote this class for me, and the compiler is storing in that class a field called min and a field called max, so that my query afterwards can use these fields to use the values that I actually passed into my method there. So this is a hidden allocation. Not only a hidden allocation of the object containing the minimum and the maximum, but if I would pass in, for example, a person and an address, I would also have the hidden allocation of the person and the address being stored in there. So some things are going on that you may not want to have in your intermediate language. Maybe in this case, instead of writing the link statement, if this is your core business logic and this is called a lot of times per second, maybe you want to rewrite this one to a for each loop that calculates this thing instead of using link to avoid the fact that you're allocating so many things. But again, measure to see if it actually makes sense to do that. A couple of other examples, task.run, for example, will also allocate hidden things. Basically the same thing, the compiler will generate a class for you, capture some values in it, and then use those things. But I'll not dive into the IL language of that one because I think some people may have a headache. I at least have a headache, so I would have a headache if I was watching this. Anyway, hidden allocations. This is really important, and I will take well, basically the one who wins the ClrMD ticket there has to say this thing as well. It should be the takeaway of tonight. Don't optimize what you shouldn't be optimizing. Always measure and see what is happening in your application. You want to know when allocations are done, where they are done, of course, as well, but you want to know when allocations are done, and you want to know if it really matters that you are doing so many applications. You want to check those things. So you want to know how frequently are we putting stuff in the heap? How frequently is the garbage collector doing its thing and scanning all those things in the heap and cleaning out those objects as well? What generation do we end up? If everything happens on Gen 0, perfect application because it will be really fast and there's no worry. If you end up on Gen 2 continuously and collection always happens there, maybe you should be optimizing some things. And then more importantly, are the allocations really introducing pauses in your application? If your application has to pause for 5 milliseconds and you're creating a simple CRUD application where you enter some data and the user gets back some data, maybe those 5 milliseconds don't matter. Maybe they do. Again, it depends. So measure. Always be measuring. You told me 8, right? Mm-hmm. This is hard.
8-ish.
8-ish. Oh, 8-ish is fine. Yeah. Being a Belgian, I decided to write a demo that is making use of beer. And I have a beers.json file. I'm not going to open this in Visual Studio because Visual Studio will hang on me for about can't I open with? Okay, let's see if it can find Notepad++. No, okay, fine. Anyway, this file is, I don't know the real size, 23 megabytes of JSON, and Visual Studio will not open it. And even Notepad++ takes its time to open it. Basically, if the file opens, we'll wait for a couple of seconds there. If the file opens, you will see it's not really complicated, but Belgium being the beer country, we have lots of beers, and probably the Netherlands have a lot of them as well. I'm a beer fan, and I'm pretty sure the Netherlands have a lot of them as well. And this file contains the name of the beer, and it's really small, and I'll try to zoom in without crashing Notepad++. But basically, it contains the name of the beer, a brewery of the beer, a rating, because I want to know is this a good beer or not a good beer, and the number of votes, so that I can calculate if the rating actually makes sense, because it's only one guy or one girl who drank the beer. Maybe it's not interesting to account for the 0.2 rating, for example. So I want to know those things as well in the application. Now, imagine I'm building a mobile application, and this JSON is generated based on a database, and I use it on the website to show it at some point, and I try to refresh this one in my application every couple of minutes so that I can update the values and so on. Typical scenario that you could see in an application. Let me close this because it's, yes. So what I did was create 3 versions of loading this thing into memory using JSON.NET. One is the load beers insane methods, and that is not, as the name implies, that's not the way you want to do this. What this thing does is what all of us like doing, jarray.parse, here's a big string. It's easy, right? It's nice to do, but it's not the best way, because it will mean that I'm loading all the data from my file, 23 megabytes, into a string in .NET. Then I'm parsing a J array of that, so that's 23 megabytes converted into a JSON array with J objects and J properties and things like that. And all those properties have a name, and sometimes the name is name, but there will be whatever amount of data that is in the file, the strings will be duplicated for that amount. So that's probably not what you want to do, and you will probably see that the 23 megabyte file in this case will represent 500 something megabytes when you load it this way. So this is not the way we are going to do. We are smart, we learned from past mistakes, so we write this version. Basically what we want to know in the application is for every brewery, we want to store all of the beers of the brewery with their name and their rating. That's what I want to do. So I'm not even loading all the data, just want to have a list of breweries, all of their beers, even if it's only one, and the ratings of the beers in two dictionaries that are embedded into one another. What I'm doing is creating a JSON text reader, which will stream my file. It will basically create a window on my file and roll over the window and load whenever it actually needs to load something, so that I don't have to load the entire string at once into memory. So while I can read and I see that an object is in there, I know that I can actually load an object. I can further optimize this one, but in this case, for every single beer that is in the file, I will just parse one object, and at the end of my if here, the object will go out of scope, and it may even be collected, so it will not really show up too much in the profiler. So I'm loading the beer, loading the brewery name, beer name, rating, then adding the dictionary of all the beers for this brewery, and then adding those things, and at the end of my methods, I will have my beers populated with all the beers that are in there. I'm not going to run this because it takes almost a minute to run, but I did profile this. If you look at my load beers unoptimized, you will see an interesting memory pattern. You will see, of course, that allocations go up at some point, so you will see that I'm allocating things because I'm loading the files into memory. But you will also see that there's a couple of really interesting things on there. First of all, the gray stuff you see here, let me zoom correctly. The gray stuff you see on here is unmanaged memory. So that's really the stuff that you are not allocating. That's what the .NET runtime is doing. And apparently loading all these different strings and so on means that there's a lot of unmanaged memory being used and so on. You also see that I have Gen 0, which is the blue thing, Gen 1, which is the red thing, and Gen 2, which is the green thing. And you see Gen 2 is increasing. Reason is I'm loading all these things into memory. The garbage collector runs whenever the if statement happens that I told you there, apparently. And the objects basically end up on Gen 2 in this case, which is fine. I want to have this available. It will live for 5 minutes and then I'll reload everything and again. The thing is, after that first snapshot, I did a reload of everything there. So what you see is that I'm basically doubling the memory usage that I have. And when everything is loaded, I'm replacing my current dictionary with a newly loaded dictionary. And then everything goes down, garbage collector runs, but I still have, this doesn't look too good. I want to basically load them once and then flatline all the way because a rating may change, but it's not going to be that every 5 minutes a new beer will pop up, although in Belgium and with all the microbreweries, you don't know. But typically it will not be a lot of data that happens there. If we look at the snapshots and compare memory traffic, you will see that it's mostly strings and J properties where I'm allocating and collecting bytes. So basically you see that in the first snapshot even, the first load of the things that I have there, I'm allocating 58 megabytes of strings and collecting 41. So I'm introducing a lot of overhead there and giving the garbage collector 40 megabytes of work where apparently 18-ish should suffice to load these things into memory. So that's why I used a technique called object pooling. I told you that I am basically replacing my beers array every time, my beers dictionary every time I'm loading this thing. So that basically means that I'm having at some point 2 dictionaries in memory. I want to have one. I want to reuse my existing dictionary and just update the values that are in there. So I wrote another version, which is almost the same, except that instead of just adding stuff to a new dictionary, I'm reusing my old dictionary, checking is the brewery already in there? If yes, find the beer in there. If yes, update the rating. If not, then you can of course add it. But I'm really optimizing the way that I'm doing this and reusing the one that I loaded initially. By doing this, my snapshot will look really, really different. You will see that I'm actually flatlining there. I'm loading all those things once. I cannot go past that because I want to have the data in memory. But after that, whenever I reload and whenever I collect after such a reload, you will see it's almost a flat line. Some new data may be loaded and stored in this dictionary, but all in all, there's not a lot of memory traffic. And if you see a nice flat line like this, the garbage collector will not have to collect a lot of things because the object set is not increasing and decreasing as violently as we had before. If we look at memory traffic here, you will still see that there's a lot of strings being allocated and collected and so on. But the memory traffic is much flatter and I'm not allocating as many things. And as we've seen, when does the garbage collector run when you allocate a lot of things? Well, the first time the garbage collector was pretty much running continuously, and it's still doing that in this first part of the chart here. But afterwards, it will run less frequently because I'm not allocating as many things that I was doing before. So that's the technique called object pooling. So do that. It's actually a design pattern. You can read about it. Also, the ASP.NET people have been using object pooling quite a bit in ASP.NET Core and ASP.NET Core Web APIs and so on. And they actually have an issue where they describe the changes that they made to make it more memory efficient there. So really interesting posts. Right. One thing, don't just start optimizing. The garbage collector is really fast for those Gen 0 collections and so on. So use the knowledge that it is really fast for that. If that's your scenario and you are not moving on to generation 1 or generation 2, it's perfectly fine. Let the garbage collector handle it. It's only when you see things are not as efficient as they should be, then you may want to look into optimizing things. Know when those things happen, so measure. That's the main takeaway there. Right. How much time do I have left? 10 minutes. I'll cover strings quickly because I have the ultimate geek out for you as well. Right, strings. Strings are objects in .NET. Even though they are nicely lowercase string and they look like an integer or a boolean or whatever, they are really objects. If you look at the source code for string in the .NET reference source, you will see that it's basically an object that holds a char array of every single character in your string and a length property. So it basically caches the length of your string in there as well. Not very complicated, but that's the way it works. There's also a bunch of operator overloads in there. It's a really interesting class, by the way, if you're interested in the .NET source codes. There's a bunch of operator overloading in there to make it behave like it's a value type, but it is really an object. So whenever you create a new string, you are allocating memory on the heap and the garbage collector will have to keep track of it. That means if you create a new string using the constructor, anyone ever did that? For things like dividers in console applications, it actually makes a lot of sense because this is a nice string of 25 dashes there, so nice free tip. There you go. So that allocates a string. If you create a substring of an existing string, your existing string is in memory, but the substring will be in memory as well as a separate string. So calling .substring or .split or whatever will create a lot of strings. If you are reading a CSV file and you have 100 properties in there or 100 fields and you do a .split on the semicolon, you will have 100 strings plus your original in memory. If you fetch something from a website somewhere, that also will generate a string. By the way, this is not an allocation, but the get string async is an allocation because you are getting the response back from the server. Right, how do you measure string allocations? Well, again, there's profilers for that. And just because I'm really insane, I attached my profiler to Visual Studio this afternoon. And if you look at the string duplicates, which is a feature in the profiler that gives me all of the duplicate strings that are in there, you can see that WPF is creating a lot of duplicate strings. So even if you have the same string, if you're loading this from a different assembly and so on, the string will show up multiple times in memory and you're basically wasting memory. Typically, again, not an issue, but maybe you want to measure, because if you see 20,000 or 20 million strings that are the same, something may be wrong in your application. But this is typically a good way of looking at those things. By the way, Visual Studio, just start a new Visual Studio instance, has 222,000 something strings in memory. Quite a bit. So yeah, thanks for bearing with me there. String duplicates. We saw that there are actually string duplicates in memory, even in Visual Studio, and every application in .NET will have them. If you create a console application that has no code and just runs and immediately closes, you have duplicate strings in memory. The ones that you will see are all the things that are in system.globalization, so you will see Maandag a couple of times, you will see Dinsdag a couple of times, you will see September a couple of times in there. So all those things are duplicated in that namespace, and by default your application will have duplicate strings because of that stupid namespace. Are they bad? No. Again, the garbage collector is really good at cleaning out strings and so on, and they are relatively simple types because they're just a character array and a count, so it's really quick to clean them up. But if you are building, say, a search engine or something, and all those strings end up on Gen 2, it's okay to have them there, but maybe it's not okay to have them there because they waste space and they also have to be rechecked every time the full garbage collection runs. So it may make sense to look into optimizing that. Now, good thing is that not all strings are on the heap, and not all strings are duplicated. So if you would write this code, A equals hello world, B equals hello world, and you would run these two lines of code underneath, what will be returned? Anyone? I'm comparing both of them, so it will be either true or false on line 1 and true or false on the second one. This one will actually return true, true. The reason for that is that the compiler will see that hello world equals hello world in value, so it will pack them up and both variables will basically reference the same variable. So that's a nice optimization at compile time to not immediately duplicate everything that is in there and really squish them together and just have one string in memory. If you want to geek out, and I tend to do that sometimes, if you open up any decompiler, there's a couple that will show you all the headers that are in your assembly. You will see that there's a special header in the metadata of your assembly called US, or user strings, and it will hold a pointer and the string value. Now, we already saw in the intermediate language codes that you can see whenever a string is loaded and so on as well. Basically, when you do a LD-str, load string, .NET will just look at this table and load the string from this table and reference it using this table. So it will not allocate it in memory, it will reuse whatever is already in the headers of your assembly. So hello world in my previous example will be in here just once, and if you would decompile further, you would see that A and B would point to the same string from this user string table. So that's good. Now, basically taking one URL and appending a slash at the end. Even though I run this 1 million times, I will have my original string in memory and then one additional string and 1 million variables pointing to that same string in memory. So that's really efficient. Now, why are not all strings interned by default? You would think maybe it would be interesting to do that. Actually, Java has a garbage collector that does string deduplication interning for you at runtime. If you want to write your own garbage collector for .NET, it may be interesting to write something similar for .NET as well. But anyway, why are they not interned by default? There's always a trade-off between CPU and memory. Because I have to follow this reference to check if the string is already interned, when I'm allocating something using string.intern, I have to check is that string already interned, so I'm wasting some CPU cycles there. May make sense, may not make sense. The one thing why string interning is not always what you want to do with every string in your application is that the strings will not be allocated in the heap. They will be allocated on a separate sort of heap for those types of strings. The reason for that is if you're using string interning, you don't want the garbage collector to touch those strings because you may still have references from somewhere else to that string. So that's why those strings are allocated somewhere else and they will never be garbage collected. That's a good thing because the garbage collector is not wasting time on that and you know that the string is always going to be there. But it's also a bad thing because the string is always going to be there. So if you store all the names of the months in there, if you store all the countries on the world as an intern string, may make perfect sense. If you want to store all the different names that exist in the Netherlands in intern strings, that's probably not a good idea because people with a very exotic name will be wasting space in memory forever, even though they change their name because they may change their name. So the memory will be allocated forever. You don't want that. As a rule of thumb, I can say if you have a lot of strings that have to live a long time, but are not really super unique, interning is always a good thing to do. If you have a lot of long-lived strings, but many unique values, you probably don't want to intern them because they will be wasting space in memory and they will never be collected. And if you have lots of short-lived strings, just let the garbage collector handle them. There's no point in interning those, unless you know they will become long-lived, of course. But again, measure, see if it makes sense, and it could make sense in your application. But for many things, trusting the garbage collector would be the better approach. Right, I have 2 more minutes. Good, I'll make it 8, 7, I'll try. We've seen at what .NET does in terms of memory management and the garbage collector and so on. Now, it would be interesting to see how the heap is really structured, how .NET stores memory internally in this big chunk of memory that it reserves when your application starts. And we can actually do that. But let's first think about how we would build our own language with a type system and managed objects similar to .NET. How would you build a managed type system where you store things in memory that is both CPU as well as memory friendly? The two last things are really difficult because those typically contradict one another. But I would think maybe something like a relational database in memory. Of course, it's not a SQL database, but I would have to write something myself. But I can create some table that stores type information. I have a person, and the person has an age, a name, an address, and so on. Just the knowledge that I have a name, and the name is a string, an age, and the age is an integer. A table containing that data. Then I would probably create another table that contains just the values and a pointer to my type information so that I know when I see Maarten there and it says it's field ID 123, I can link to the type info and see, that's the name that is Maarten there. So I can write some sort of a join statement there. I would probably also store some table where I have the method names so that when I run a get name or set name, which can happen in your application or some other methods, that I know what the address of that executable thing is so that I can actually execute it. And then probably some inheritance information and lots of other things, but basically a couple of tables containing type info and the actual values and join those together at runtime. Seems reasonable because it deduplicates the data. I'm normalizing my data model so memory will be friendly, and linking those two together is not very, very CPU intensive as well. Turns out it's a good approach because that's also how .NET does it. Things that are allocated on the stack, if you store some integer there, you'll basically have 2 tables, the main instance ID pointing to an address that has a value, so your integer will just be 2 tables. If you store something on the heap, you actually get this, well, really a lot more, but you get something like the relational database that I was thinking about. When you allocate something, you will get an instance ID and a pointer to values that are in your class. So I will have my age in there, my name in there, and so on, but also a link to the RTTI address, the runtime type information table, so that I can get information about what are the properties, what are the types of the properties, and so on, and basically make sense of what is in memory. That's how .NET does it. There's a couple more tables, but in a nutshell, this is how that happens. Well, the good thing is we have that information, and there is a NuGet package, ClrMD, or Microsoft Diagnostics.runtime, that gives you access to this structure. You can connect to an application, look in the heap, get the type information, follow the pointer, get the properties and things like that. So that's kind of nice. Long definition on their website. To me, it's linked to heap. I get a nice, kind of nice query language on top of my memory system. In case you are wondering why would you do this, I will cover that in a bit. I'll first show you what is possible. Since I'm kind of limited on time, I think I'll do the introduction and the actual demo at once. So I have a project here, or a solution that has two projects. I have a ClrMD Explorer, which is where I'm doing all the link to heap stuff. And I have a target application that is a very simple application that allocates a string, that writes a string to console, then starts a timer, has a clock class, and then does some things like printing the current time. So if I would run this one, such boring demos, I know. But anyway, this one will run and it will give the current time. So now I can even see that I'm over time by 2 minutes already. So awesome. My application is useful.
So 6 o'clock there. So basically, you have 2 hours.
Fine. Then I have the other application, and that application starts my demo process. So basically what it does is it opens my ClrMD target application and starts the process and returns the process ID so I know where I can connect to. Now when I run my Explorer, I will give my application a couple of seconds to run just to print some timestamps so I know what the current time is. And then I will attach ClrMD to the process. The way I do that is by saying data target.attach to process, the process ID. I give it a timeout of 10 seconds, so it gets 10 seconds to do its magic and connect to this thing and get the information. And I'm attaching in an invasive manner. The reason for that is the same reason as why the garbage collector cannot run asynchronously with your application. I want to see what is in memory, so I want to pause the application and not have anything change until I'm done looking at the current memory space. I don't want it to change continuously. There's another flag that you can give it where you get a more interactive way of looking at the memory space, but it will give you exceptions if you call some methods to look into some variables and things like that. So invasive is, with this tool, probably the good way to go. In case you're interested in this afterwards, it attaches to processes, but also can read crash dumps, for example. And that's interesting because I can analyze whatever was in memory when a crash happened in my application. But anyway, when I run this, I can get my current CLR version and connect to my app domain and then dump some information. I'll just run it so you can see what happens. My application runs and then I attach. The first info I get is info about my current CLR. So it looks like my system is running .NET 4.7 and it's using a DAC file called this one. The DAC file is important because that's basically the data access layer or the data access control file that gives me the way .NET structures the data in memory for this version of the framework. ClrMD will download that file for me, so I don't have to worry about that. If you have been using WinDBG, for example, you would have to typically find this file yourself, and that may take a lot of time. And if your server is on a different version than your machine, it's a headache. If you have ever tried it, it's not funny, and here it is kind of funny because it just works. Then I can get runtime information. I can get information about the current executable, the configuration file it's been using and so on. So basic .NET stuff about my running application. And then I can look, for example, at the number of threads that are in my application. I have one foreground thread, which has this stack trace. So I can even look at the stack trace of my current application. Then I have some background threads that has the debugger attached, because that's what I'm really doing with the ClrMD thing. I'm acting like a debugger to look into these things and print those things. So I can look at that information as well. Another thing that I can do is look at all the values in memory. So you will see that there's a lot of strings, and I can look at the values of those things. And you will see, for example, the date formats. Object with this ID is of type system.string is 84 bytes and the value is this string so that I can format my date. So I can really look at what is in memory. The way this works is that I can dump objects on my heap and basically enumerate all the object addresses. Remember the first table on the slide? Enumerate all the addresses in there. For every address in my current generation, I want to get the object type. This is basically make the trip to getting the information about my objects. Then I get back my type. If the type equals null, I'm not interested because it's going to be .NET internal. If it is not null and I really get a value back, I can start printing the type of the object, for example. Then if I want to look at the value, I can make another hop to get the value based on my type information for this specific object at this specific address. So I can make those links that I showed you already in this relational database kind of way. I can make those links in my codes when I want that information. What else do we have in there? So I can dump those things, and I can do things like analyzing string duplicates, for example. That's another one that I have in there. I wrote something that would check for duplicated strings in my current memory space, and you can see that May, for example, has 16 usages. I have no idea why, but it's duplicated 16 times in memory. The days of the week are in there 8 times, the months are in there 8 times, and so on. So you see those duplicates are already in memory. The way that I created this table was quite simple. Just create a dictionary of the value, number of usages, walk the entire heap. If it is a string, compare the values and just increase the counter. So it's not rocket science, basically looping the entire chain again. Now, what is more interesting, this is kind of interesting because this is almost what a profiler does. But what is also really interesting is that I can spot memory leaks using this tool. I will give you 10 seconds to spot the memory leak in this piece of code. I'll zoom out a little bit so you can see everything there. Yeah. What's the memory leak? I'll give it to you. So basically, I have a timer class, which is .NET Framework, and I have a clock class, which is my thingy. And I'm instantiating this timer and saying that every second I want you to call on my clock the onTick methods. Then I created a using statement and a disposable that should dispose my clock. The problem is, even if I would run gc.collect at this point, the clock will never get collected. Reason for that is my timer is still running and still referencing my object's onTick method. So the object will always stay in memory. Using a profiler, and again, it's not memory. But if you look at it, there's a way to inspect in a snapshot all of the objects that are in there. And if I search for my clock, I can look at key retention paths. And the profiler will actually tell me that my clock is still in memory at this point because it is held in there by a callback on my timer, which is in there and which is in there. But I get this entire hierarchy on why this object is still in memory. Nice thing is with the ClrMD tool, I can also create something similar where I just walk the entire heap a couple of times, find all the pointers to my clock, and give me a nice, even if I add some bit mapping there, a nice diagram showing me my clock is in memory because of a timer callback, a timer queue, etc., etc. That's kind of nice to do this. Kind of nice. But why? That's a really good question. You probably don't want to start writing memory tests like this if you don't know what you are testing. But I actually was working on one of our products in JetBrains, and our build server told me that I created a memory leak. The memory leak that I was created was very similar to the one that I just showed you, basically in our IDEs that we built, so